Hello and welcome to another Würth Elektronik webinar. Today's topic is SMPS, or as you can see, efficient EMC and power converter design. I'm Markus Eberle and I will moderate this webinar today. I'm very pleased to welcome today Loran Völke, who is working as Field Application Engineer and Business Development Engineer at Würth Elektronik ISOS. So today we are presenting live from our new studio and we are recording right now this webinar for you. So this means that you cannot ask us questions today live, but nevertheless you have the opportunity to ask us the questions with the chat function and we will answer them in the next few days for you. So please feel free, tell us your questions and yeah, we will come through to you. And also you can contact us always with our email addresses, as you can see it here, webinarteam@we-online.com or directly to Laurent. After this webinar, we will also send you the recording of this webinar as well as to the presentation, and yeah, you will get this also from us. So now I'm happy to welcome Laurent and yeah, wish you a very good webinar and yeah, have fun.
Thank you, Markus. I'm very pleased as well. My name is Laurent. I prepared today some little topics about how to make a power supply EMC efficient and also power efficient. Even if you build a DC-DC converter, you know that a DC-DC converter can generate something like conductor emission noise. Many of you have already this experience. And if you make a perfect layout, perfect ground plane, it will be not enough to pass all the EMC tests. And if you have a scope only with 300, 350 megahertz bandwidth, and you're looking for qualify this product until 1 gigahertz, it will be almost impossible. Even if you have a 1 gigahertz scope, and you're looking for 1 gigahertz noise, it won't work. You need 3 times more bandwidth like the haunted signal. So can you imagine you go to your boss and you say, hey boss, I need a 3 gigahertz scope now? Few sport cars and few house villas are included in this price. So you will need something like a spectrum analyzer at least. If you qualify a product for a European market, you have to be compliant with the CE marking. CE marking, it's also something even is in UK, not European Union anymore, but they use the same levels and the same qualifying system. You will need to qualify your product and to make the EMC testing. If you look for a power supply today, almost everything somehow battery operated. And the battery, when it's charged, has this 3.6 volt charge, completely charged. You need a 3.3 volt output, so you have a buck converter, a buck conversion actually. And when the batteries start to get empty, a certain level is below 3.3 volt, so you need to boost now the voltage. So many often you will use a buck boost converter. A buck boost converter must be taken in consideration in a different operation stage, because when it's working like a buck converter, you have to focus more on the input for the noise. As soon you operate like a boost converter, you have to focus on the output, because the output will be your EMI noise. In buck mode, always the input. In boost mode, always the output. So a simple topology would be something like a zeta or SAPIC topology. The difference between zeta and SAPIC topology is the position of the switch. In zeta, you have the switch and then the inductor. Zeta topology, you have to take care for the critical loop on the input. Less for the output, more for the input. If you use a SAPIC, like I told you, you have the SAPIC different, you have the coil and then the switch, you have to focus more on the output. The output is more noisy like the input. So it depends now on the topology. If you use a simple non-synchronous buck converter, always a non-synchronous buck converter is noisy on the input. Why? You charge the energy into input capacity, and through the switch and storage inductor, you put this charge to the output capacity. The designer, which is also maybe sometimes radio amateur, or you build something with antennas, you very very fast you realize these two capacitors with the switching in the middle, actually you build here something like a dipole antenna. You have the capacitor and you have this wire here, and this is the connection from input capacity to output capacity, the noise source of your DC-DC converter. If you take a near field probe and you go to this area, you will see this is the most emitting zone. So please don't push the auto routing button on your layouter, because when you make auto routing, you will not know where is this routed. And take care that this is made manually, and keep this track short as possible and less antenna as possible. 1 millimeter PCB track is 1 nanohenry inductance. Consider that, and if you do not push the auto routing, you may have the luck that you have less PCB rerouting or redesigning. Now, if you look on the output of this DC-DC converter, you may say, okay, I'm switching at 500 kilohertz, but I see in the EMC lab 250, 300 megahertz noise. Where is it coming from? Well, actually, the diode is also not ideal. It has also parasitic. The capacitor has parasitic components. Inductor has parasitic components. And in a very high frequency, can oscillate here and can start to make a ringing, which is in the EMC lab, can be with a receiver, and you can see that you make noise. So try to use maybe a synchronous buck converter to emulate the ideal diode, and try to keep this short as possible to not have any resonant points. Now, also for the controller and the MOSFET, you have to consider that like a digital connection, because actually the controller is transmitting a digital signal. It's maybe not a very USB signal, but it's a digital signal because it's rectangular. And because it's a rectangle signal, you have to consider like a digital signal, and you have to take care about the back path, about the impedance of the tracks. So try to keep the tracks identical length, try to keep that close to each other, and then you may have less problem with this fast rise time, which can occur from the controller to the MOSFET. I did discuss with Ken Hyatt, which is a EMC guru. It's an absolutely big guy in the EMC world. And he did consider in the same way that actually we can define an EMC formula, because as more current you drive, as bigger will be your EMC problem. As more area you enclose in this noise field, as bigger will be the EMC problem. As higher frequency switching you are using, as bigger will be the EMC noise. So this is the trick. Even it's not a mathematically correct formula, but this is something which you can realize: more frequency, more higher switching frequency, more EMC problem. And then you can say, okay, if I take in consideration this formula, then maybe it's the shortest path theory, not always the best one. Because sometimes it could happen that you have a noise source and you have the load, and the shortest path to source to make a short of this noise, you will enclose a big area in the EMC field. And sometimes it's like when you're scratching your head, you can scratch like that, or you can scratch like that, and you have the same effect. Same as in EMC. You can try to reduce this enclosed area, even it's not the shortest path, but you have less enclosed area in the noise path, and then you have less EMC problem. Try that by your next design. Try this as well. The next is how to select the right component. First of all, take care about the DC bias effect. Remember that the 100 nano capacitor by 50 volt, it won't be 50 at 50 volt 100 nano. Even the data sheet is written like that. It means it will withstand 50 volt, but his 100 nano, it's far away from that. Exception if you take NP0. The next point is, again, the parasitics. Don't simulate ideal inductor and capacitor. We cannot build them. You get free of charge from all the parasitics. We don't charge you for them. But please consider the parasitics, because they will be occurring if you are using models of ideal components. Please use library with the parasitics. The next is the temperature drift. Every sintered ferrite core has a temperature drift. If the inductor is measured in laboratory condition at 20 degrees Celsius, you will have a different value, like at 85 degrees or by minus 55 degrees. So consider this sintered ferrite, they are drifting. If it's an alloy, Not if it's a sintered ferrite, it has a drift. And consider always the impedance versus frequency. You select the chip with ferrites not because of 100 megahertz has 100 ohm. Look on your spectrum at which frequency you need this impedance, and don't choose only because of 100 megahertz. Choose according to the impedance curve, to the frequency, to the right position. And the last thing, the most important today, if you select components which are available from stock. At Würth Elektronik, we have a high service degree, 99%, and we are delivering almost like you wish the component from stock. But sometimes you can have a problem that you can order it, it's existing component, but the delivery time is in 2 years. So maybe you should double check if this component is a standard component from stock, and you can build your design. If you want to simulate these components and you want to know how is the behavior of these components, I can recommend a Red Expert. You can access that on the website. This is a free tool. If you click on this link which I put here, you can already see what's happened to this inductor when used in terms condition. You put your input voltage, output voltage, switching frequency, and the current, and you choose the component, and this is measured values in different points, and you can see what happened to this inductor. Is saturated, not saturated, self-heating, how much is self-heating. All this is in Red Expert available and free of charge. Of course, also LT-Spice, Altium design files, different libraries are already on the data sheet. Not only just the data sheet, you can just click on and download it. Another issue is if you want to filter something, if you have a EMC problem and you don't know how to calculate, or you want to approach a fast filter calculation, you can choose a simple LC filter. Already you have the parasitics included. You know what is the insertion loss. You need the input impedance, output impedance. Very easy in Red Expert. Just easy to check it and just add to your basket, and you can order it free samples. Let's talk about input capacity. What happened at input capacity? You choose a X7R capacity. What means X7R? Lower temperature minus 55 degree, 7 plus 125 degree, and R means the tolerance, plus minus 15%. Of course, depends on the dielectricum. It will be different, like X5R or different. It's just that don't tell you about the capacity too much. But if you consider this different capacity together and you look on the same value, you see that X7R to X5R have a big difference by the DC bias voltage. Like a 50 volt capacity, NP0, you pay a lot, but you have no drop of the capacity. If you use a X7R 50 volt and you are using at 25 volt, you have almost already more like 20%, almost 30% drop of his capacity value. If you choose a X5R will drop more like 60-70%. So it is just the information that this capacity can withstand this 50 volt, but doesn't give you information that it will be 100% half the value. So think about by the capacity selection, if you need 100 nano, which dielectricum you have to use. The next thing is in time, deterioration in time, only 1,000 hour. Only after 1,000 hour, different capacity have different behavior. NP0 doesn't drop at all. Already X7R drop, X5R drops, and capacity Y5V, which we don't have. That's the reason why we don't have that, why we don't build that, because it's, you can put something on a PCB to have more kilo, you have more weight, but no effect. Please consider that ceramic multi-layer capacitor, not Tanta, ceramic. Drifting in temperature is not a big deal. NP0, X7R, or X5R doesn't affect so much, but Y5V, this is the reason why we don't have them and make no sense to use them, because they have temperature drift, they are not stable, they're just some components. You pay just for to have something nice on the PCB. How to get all this information? Again, please look in this Red Expert. You can find all this value. All these values are measured, and you can find here, you can select X7R dielectricum 1 microfarad 50 volt, and then you realize, okay, the impedance is same, the ASL is not so big deal, but the big deal is the package. If you compare the different packages, if you compare like same dielectricum X7R 1 microfarad 50 volt, and only by package 12 1812 to 0805. You can see that at 1812 or 50 volt by 30 volt has maybe 15% drop. 0805 have already almost 38% drop. You cannot imagine how much is 0603. So that is the reason why we don't say you should use a 0201 capacitor, because in datasheet looks everything same, very nice. But in reality, of course, if you have just few plates or two big plates by 1812, it's a big difference by DC bias load. It looks much more dirtier if you go down to smaller components. For this downsizing, what is happening, you can see here X5R, X7R, same dielectricum, different dielectricum, they have not a big drop. But as soon you go to 0603, you have a big drop by the dielectricum. So please use capacity which have worked, not just to have put something to the board and then it's not working. This is again application by step-down converter, 12 volt to 5 volt, 1 amp, 1 megahertz switching frequency. The output capacity is aluminum electrolytic, 16 volt, 47 microfarad. We record the peak-to-peak ripple on output, and this solder the capacity and solder instead of aluminum electrolytic a polymer. So take it out, aluminum, put a polymer. What happened? Polymer 16 volt, 47. Of course, lower ASR, lowers ASR, including the peaks. You have now from 400 millivolt drop the peak to 50 millivolt. Only just changing the output capacity. Now, this solder this capacity as well. We have pads which you can solder even a multi-layer ceramic. MLCC 16 volt, 47, peak to peak 40 millivolts. Very easy, just changing the capacity. Even 40 millivolt is too much for a Bluetooth module or RF module. Maybe you should put additional filter to go down now, like less than 10 millivolts or even 5 millivolts will be perfect. Now, the RF module doesn't like to have too much ripple on the voltage. Now, one of my colleagues had a nice project. He had to design a 100 watt DC-DC converter, buck boost converter, and the customer asked him to supply him 3 different solutions. All these 3 different DC-DC converter should fulfill EMC conductor emission, radiated emission, and should have efficiency minimum 95%. And then these 3 designs should be like one, low cost as possible, but should fulfill the request. The second, a compromise, not so cheap, not so expensive. And the third one, no budget limit. This is a dream. I never had this opportunity. Nobody ever gave me an opportunity to build something with no budget limit. Maybe I should work for some petrol mining company or something like that. Because he decided to use the LT3790 on the data sheet. You can see already the efficiency is quite very good. He go by this analog chip and then decide for the first designer low cost to use the higher switching frequency, 600 kilohertz, because has less inductance value and less capacity value, and using only a 4-layer PCB, not because of the DC-DC converter, because he has also a logic board with a QFN package, and he will need a 4-layer PCB anyway. So, but to save money, put components only on the top side, no components on the bottom side. 1 volt, 1 ohm gate resistor additional, and then decide to use the MOSFET from Infineon. The package is not optimal for the good temperature conduction, but also the ASL is relatively high. But it fulfilled the requirement from his design, and he decided to go by the Infineon chip. Then, using the Red Expert, he decided for the selection of the inductor. You can see he decided XHMI, 4.7 calculated for the software. He decided for 4.7 using these components in boost mode. He will have a temperature rise of 16 Kelvin. This is not so big, not so small. In boost mode and buck mode, the same inductor will generate also 16 Kelvin, and the peak current is 5.7 amp. So he has a saturation point at 27. Everything safe. Nominal current also 13 amps, so it will be in a safe mode. So he decided to go by this inductor 10 by 10, very small DC resistance, only 5.4 milliohm, should be okay. For the input capacitor, he decided, okay, I will need a ripple on input of roughly estimated 100 millivolt peak to peak by 600 kilohertz. He will need 14 microfarad. So he decided to go by using 4 times 4.7 and put additional aluminum polymer bull capacitor here for no swing on the input, because to have this energy storage. That is for the input. And for the output, you say, okay, I will go also by the output using maximum 20 millivolt output ripple at 600 kilohertz. I will need again 16 microfarads, so he will go again by 4.7, considering this drop of the 50% DC bias by the output of this 18 volt, 20 volt. And then he go by 16 microfarad should be fulfilled, 4 input multilayer, 4 output multilayer, and additional 220 microfarad capacitor for fast transient response. So this is the design, including in the LT spice, even the parasitics. You can see this is the PCB parasitics. And if you include in the parasitics into the LT spice, you may have an accurate simulation. This is the simulation. When he made his PCB, he compared with the scope what he did measure, and then you can see the simulation was not far away from the reality what he did measure with the scope. Now, this is the reason why in the simulation you should use always models for the components, which including the parasitics, because else you will cheat yourself. You make nice simulation, but it won't work in the reality, in the real world. Now, because we have this FFT on the LT spice, you can already with the LT spice pre-estimate your noise. You can make a FFT from 150 kilohertz to 30 megahertz, and you can include this limits line for the EMC measurement, and you can see if you want to reach this 40 dB line, which is the EMC law request in conductor emission, you have to damp at least 50 dB. Now, you need the calculation of the filter. This is the setup how we did measure it with the own setup with a small listen from Langer Elektronik, and then we have this electric simple resistance load. This is the scope using on a very good ground plane, and we decide, okay, we need a good filter for that. The setup could be look like this. This is with the Langer NBB21, which can be used up to 1 gigahertz. So the input filter need to be at least, you need an inductor, you need a capacitor, and you need a G-bit farad. It's a T filter. This is for conductor emission differential mode. But because you will connect cable on input and you will connect cable on output, this is how the measurement will take in an EMC lamp. The consideration will be clever to put an output common mode choke and also an input common mode choke to cut these antennas, which is during the measurement can occur. So this is actually the component that he did choose for the input and output filter, and very easy to simulate in LT spice. You have the models, and when you simulate, you realize fast, okay, LC filter will be not enough. If you want 50 dB, you need a little bit more. So you need at least T filter. So decide for the T filter input and T filter for the output, little bit different tuned, and LC filter will be not enough. So like I told you before, the common mode choke, you will need to cut the antenna on output and cut the antenna on input, because you have wires. And these wires are antennas. And you switch in the middle. It's a good thing to put this common mode choke in advance, and you save the money for the snap-on ferrite, because more expensive. Now, this is the final schematic. You can see here the common mode choke. You can see the input filter, input capacity, output T filter, and output common mode choke. So we have the first design. So make the layout. In the layout, he did consider the high current path to be a little bit separated for the control loop, because you don't want to go with the same current in the same area where you want to make some feedback. You don't want to make your own EMC problem. So he decided for the big current to make polygons and the small current to have one single connection on the PCB. And because of the 4 layer, he can use layer number 2, 3, and like a ground layer. Design B. Design B is a compromise. Not so cheap, not so expensive. He goes a little bit slower in the frequency, not 600, only 400 kilohertz. And he decided for the 400 kilohertz to use a 6-layer PCB, not because of the power supply because of the logic board, because he don't want to squeeze everything, so he have to make some little more spacey, and then he can put some components on the top and some components on the bottom. It's a big jump from 4 to 6 layer by the PCB price, but not that much. It must be some benefits. For the MOSFET, he changed now to Texas Instrument. He decided for this one, he had a much better temperature connection, have a very small RDS on. The RTH is much better, so decide for this MOSFET. For boost mode, he calculate again by the 400 kilohertz. The inductance have to increase because now no more 4.7 microhenry. Now it's 6.8 microhenry at this level. The delta T is now 14 Kelvin. Before it was 16 Kelvin. It's not a big issue. 2 Kelvin less plus minus is not a big issue. In buck mode, same. Okay, the same inductor, 6.8 microhenry. It generates 14.7. 16 was before. Not a big deal. The peak current is 5.7. We have here saturation point 46, far away from the saturation point. He decided to keep the same family, just increase the size from 10 by 10 to 15 by 15. Before had 4 milliohm, now he has, before he has 5 milliohm, now he has 4 milliohm. It's not a big issue, just 1 milliohm increase, also decreasing of the this resistance. I don't know, it's a big benefit. Anyhow, he decided for that. For the input capacitor, instead of using 4 pieces MLCC, because of the frequencies, he goes by 6 pieces. So by 6 pieces, he will reach 23 microfarad. Now 21 is a request calculated, and he goes by 4 pieces, the same like by design A on input. He put additional this bulk capacity 68 microfarad additional. For the output, because has 6 on input, he put 6 on the output as well. So 24, the calculation by 20 millivolt ripple, it will be 25, so what plus minus 1. He add additional the 220 microfarad again for the transient response. Now, the filter, this different stage, how it is made. The first inductant capacitor is requested for frequency between 100 kilohertz to 5 megahertz. The next stage, the chip bit ferrite, and the next capacity is the small value. It is a differential mode filter from 5 megahertz to 30 megahertz conductor emission. And the common mode choke is actually requested for common mode noise, like radiate like an antenna. And this is the reason why he put on input and output as well. So this is how the filter was considered. Now, in LT-SPICE, you have the models for the common mode choke, for the ferrite beads, for inductance. Already you can simulate that, and you can pre-estimate the losses. By 100 watt, you can really fast see that adding all this resistance together, you may have already 2% losses only on the filter. 1 watt and 1 watt from 100 is already 2%. So your efficiency, even if you have a perpetuum mobile, because of the filter, it will be only 98%. So if you are scratching on this 95% efficiency, you have to consider also the resistance on the filter, because sometimes you could destroy the efficiency only because choose the wrong component and save some few cents on the component. Now, this is how the filter looks in his simulation, which is more like 50 dB damping, so looks very good. And this is the final decision of the capacitors and input-output capacitor, and additional this chip bit ferrites on the V in, on the V in on the chip, because it's also important to filter that you don't have a own EMC problem already on the controller. And looks not bad. Make the PCB by 6 layer, component on the top, component on the bottom. Again, polygons for the big current, small current loops with one single connection to the main ground, and then you have the bottom side, you put the FET, the air sense there, and some Schottky diodes as well. Well, that is how it looks, the capacitors and output and input very close to each other to not generate antennas, like I told you before. So that looks not bad. So this is the layer number 4, because between layer number 3 and layer number 5, you make like a coaxial connection. You can hide between 2 ground layers, because by 6 layer, you have the luxury to have so many ground layers, and you can hide these dirty signals inside. So this is, you can see, you have an internal own ground layer, which is separate from the outside, and it is filtered and filtered input and output. So actually should be a very, very good EMC design. Input filter, output filter with the common mode chokes. You have the filter also on the border to the board. So you have the barrier of the EMC here. Everything what you generate noisy, it will stay inside. And this is the ground layer about the layer 2, 3, 5, and even 6, you can consider almost ground layer. Now design C. No budget limit. Wow. Wow. Dream. Well, he decided to go to lowest switching frequency, 230 kilohertz. You will need bigger inductance, but because of the switching of lower frequency, he decided to use only 0 ohm gate resistors, no more gate resistors. A big inductor value, more capacity, so he will use the same MOSFET like design B, which was very good. For the inductance, you have to increase now to 10 microhenry, and he did choose another family HCF. And with this one, you can reach delta T of 5 Kelvin. Temperature self-heating, only 5 Kelvin. From 16 or 14 to 5, it's a big step. This is in boost mode. In back mode, even less, 4.8 Kelvin. So this is a big improvement in my opinion. And of course, why? Because the inductor, it's also bulky. From 10 to 10 size, now to 28 by 27. That's very bulky. And well, it has a lot of improvement because it has a flat copper wire, more surface for the skin effect, which is starting roughly by 200 kilohertz, the skin effect. You don't need the big copper tube because the penetration of the copper will be not that much. So at 200 kilohertz, 230 kilohertz, you have this surface, you have a much better this resistance. And for the input capacitor, he decided, okay, I did use 6 before, I put one more 7. He put 7 on input. He put also this one capacitor, bulk capacity, 220 micron input, and he put on output 2 times 220, and using also 7 MLCC to the output capacity. So it should be quite enough. And because the switching frequency is so low, he decided to not use anymore this inductor, this 1 microhenry inductance on the input. He said, I don't need it because I need only just for high frequency. In low frequency, should be enough with a capacitor. Because my switching frequency is so low, I don't need that. Okay, it's like his decision. You can see there is missing the inductance on the input, but everything else is same, just adding 1 more capacity on input, 1 more capacity on output, 2 bulky capacity on output, and the switching frequency only 230 kilohertz. Now, the layout, little bit, I would say, not a big change, only just adding more pads for the capacitor. Design B and design C, same layout. 6 layer, everything routing same, only just adding some more capacity and skipping this inductor and input and inductor and output. Okay, now we have the 3 pieces. Now we can go to the EMC lab and say, what is the EMI receiver detecting? So first of all, we connect design A without filter. So we connect directly on the PCB, these wires, and we measure the conductor emission, 150 kilohertz to 30 megahertz, and you can see 600 kilohertz. Make noise, quite big peak, is no filter, of course. And I can see here my noise is going up. And because it's going up, I don't need to go in the EMC anechoic chamber. I don't need the absorber room because I know I will not pass the radiated emission because my frequency is increasing here. So this is for sure, I don't have to waste money. But let's introduce the filter. Activate the filter, bam. The filter, it's making his job, but not good enough. I can say for quasi-peak, maybe it is plus minus, little bit or below the limit or on the limit, but already average is exceeded, so you need to improve this filter. Now with the filter on, I can see that my noise is below the level, so it doesn't go so addicted to high rise. So I can risk maybe with this design to make also a emission measuring. So go to the EMC chamber without filter, directly connected. The noise is big. I don't pass the radiated emission. But if I activate the filter, like expected, with the filter activated, it was very clever to put this common mode choke because you see I am below the limit. You can imagine you make a DC-DC converter, 100 watt, and you pass by first shot radiator emission. Conductor emission, you still have to improve. By first shot, how often happened to you? Try to ask yourself. Not so often, right? Okay, let's change to design B. Design B without filter. Again, directly connected. It's less switching frequency, only 400 kilohertz. I can see the peaks, okay. Without filter, I can already realize, my noise is less because my switching frequency is lower frequency, not 600 kilohertz. It's still the tendency to high, but I have no filter. Let's activate the filter. Now is the filter activated. What? Below the level, below the limits. I have quasi-peak averaging. Okay, I don't have so big safety distance, but it's first shot. I passed the EMC test, conductor emission. I get the stamp. And I can see the noise is quite more like 10 dB distance. Now, let's go to the anechoic chamber and check what is the radiator emission. No filter, radiator emission. Hey, okay, I don't have safety margin, but I'm below the limit without filter. About these peaks, I will come back later. They are generated by the Schottky diodes. I will show you why. So, but I have no filter. Let's activate the filter. Bam. Conductor emission, pass. Radiator emission, pass. By first shot. Good guy, good designer. I appreciate my colleague because he make a good job. Okay, let's turn to the measurement. So if you measure now with the scope on the Schottky diode, on the leg of this Schottky diode, you can see 130 megahertz, 180 megahertz, 380 megahertz FFT on this overshot and ringing. Now, if you reduce this overshot and ringing, you may eliminate this EMC problem. So this is what the EMC make, this overshot and this ringing. Try to reduce always this overshot and this ringing, making short as possible. EMC will be solved. EMC will be much less filter need. Now, design C. 230 kilohertz. What is this? Nothing. Okay, no filter. Already without filter, I have no problem here in high frequency. It's for safe. But I have some peaks here. Okay, let's activate the filter because we have a filter on. Oh, I clean everything here. 1 micro inductance should be there. The 1 micro inductance should be there because this is responsible to annihilate and to filter this harmonics. It needs to be there because else I will not pass conductor emission. Now, I'll go with this design to the anechoic chamber, make the EMC radiator emission, no filter. You see? Here, no filter, and this is no filter on the radiator emission. No need filter for the radiator emission. But I have the filter on board. I know that this comes from Schottky. I have more like 10 dB, no problem. But now let's activate the filter. Uh-oh. The filter is doing his job, but what is this? I don't have here. Where is it coming from? This is when you filter too much. If you don't need a filter, don't put a filter because you want to be nice to the sales guy. This filter is ringing. This is the sign your filter is ringing with the noise. It generates an EMC problem additional because you filter too much. I think if you skip the 2 common mode choke and you put the 1 microhenry inductance, you will be much more happier like with this too big filter. Now some measurements using our setup and compare with the measurement from the EMC lab. This is our setup in the RTO, just a simple electric load, not electronic load, and a simple listen with a good ground plane, make some measurement. So in the EMC lab, we measure without filter by design A, 85 dB. In the lab at our setup, we measure with the FFT of the scope 80 dB microvolts. It means if I improve something, I have to improve plus 5 dB better to be accurate to the EMC lab. This is without filter. With filter activated, EMC lab measure 56, we measured 53. Very funny, I see that 49 is the next peak, and we measure with our setup less than 10,000 euro investment, and this is the investment more like 100,000 euro. We can measure quite very accurate with our setup. Here I have to add additional some filtering dB because I have to be better like in the EMC lab. So this is quite not bad. I was not expecting that. Now, in the EMC lab, we measure by the filter A, by the design A without filter, the radiated emission with the antenna. We don't have an antenna, we don't have an EMI receiver, but the listen, it is calibrated up to 400, 500 megahertz. So we can try to see on the cable by conductor emission, if we can deduct, we can say maybe this is this one, this is this one. So I have to filter these peaks here on the conductor emission by setup to be nice, accurate in the EMC lab by the radiated emission. When I activate the filter, of course, if I don't have noise, I will not measure anything. This is the scratching on the noise floor of the FFT. I can say, okay, this could be this one, this could be this one, so I have to filter this area to be better here in this area. But this is not a really accurate measurement. It's much better if you have a GTEM cell and you have a nice spectrum analyzer with a good, fast sweep time. Now, if I have very, very low noise, this is design B, with the filter activated, I will not be able to measure anything. I can maybe say, that could be here, that could be this one, that's all. The rest, I don't see it because I don't have noise. If I don't have signal, the FFT of the scope is not the same like EMI receiver. Now, some measurement directly with the probes for the scope. My colleague used only just the probe put directly to the input of the power supply, no listen, and try to compare with the probe and the scope the measurement with the EMC lab. Design A without filter, EMC lab measures 85 dB, we measure 88. Next peak 68, we measure 68 as well. Only with the probe, without the listen, no line impedance stabilization network. Only a good probe with a good scope, you already can be able to reproduce the measurement from the lab. If you activate the filter, EMC lab measuring a peak of 58, we measure 52. So if I have to improve, I have to add here additional 6 dB to be accurate like to the EMC lab. Now, some measurement directly on the components. You can see here two different measurements on design A and design B. Both are measuring the gate source voltage from the FET. The one what you can really fast see on the design A, it is this ringing. When you switch on, you have this ringing. You have no nice rise time, you have a ringing on the switch on, and when you compare that with design B, you have very nice, accurate rise time, almost little overshot, no big ringing, but this ringing is exactly the EMC problem. When you see that in your measurement, and you don't measure with a pigtail, you measure with a small spring, this is also important, and you see this ringing, this is your EMC problem. You have to work on that. You have to come to this picture. The next measurement, H-field probe. You take a H-field probe and you put a spectrum analyzer and you sniffer on the storage inductor. It is shielded. You can see very small noise. Now, if you sniffer now on the high side of the MOSFET, on the input, on the trap, on the track directly, you will see this. So this is your major EMC antenna. Try to keep this track short as possible. Try to not make too long and not routing, wait, auto-routing. Please don't push the auto-routing button again, because inductor is shielded. He will not radiate. A big distance between bootstrap design A and bootstrap design B. You see the big difference because of the layout. What means little layout improvement by bootstrap. If you see that, you have noise. If you see that, it's less noise. This is the bootstrap from design between the controller and the MOSFET. I think you know which picture you like more. Now, what you can do, if you have a MOSFET, no, if you have a controller, when you have a boost input for the VCC, and you can put a ferrite on this input of the boost area, you may filter this noise on the boost loop, and we make some tests with a 0 ohm resistor, 16 ohm resistor, 600 ohm ferrite, and a 2.2 kilo ohm ferrite. And you can see the difference between the 0 ohm, which is overshotting and ringing, and if you compare that with the rise time with the 2.2 kilo ohm, only this component, only one small passive component change, you see that the red one is not overshotting and not ringing so much. It has a small inductance, few microhenry, but the switching happening already somewhere like here. So this is not a big issue of delay. The big issue it is in the EMC chamber when you make the measurement. The same DC-DC converter, only just changing one single passive component. This is by 0 ohm resistor. You can see the high noise, and the extremely high noise on the high frequency. And when you put the 2.2 kilo ohm, the entire frequency is dropping. All the noise is going down, and you have no problem here in the high frequency area. This is wonderful, especially when you have big frequency like 200-300 megahertz. You can do that by using this ferrite bead on the boot if you have a boot input. Now, thermal camera measurement on the design A, only on the top side because you don't have on the bottom side any components. You can see it's very hot. I will not touch it because everything above 60 degrees is burning my finger, so I will not touch that for sure. Make no sense on the bottom. Design B on the top, already touchable, I would say. You can feel it hot, but not burning your finger. On the bottom side, because you have top and bottom components, one MOSFET is quite hot, but it's working. Design C, cool, nice. Of course, has a lower DC resistance, the bigger components. On the bottom, again, we even changed the position of the MOSFET because we think it's a MOSFET problem, but it was not the MOSFET. It is only because of the heat sink, somehow the PCB design. But you can decide very fast which was most efficient. Of course, design C. Because it's missing his inductance, the efficiency is up to 97.5. In boost mode 96. By design B, everything included, but he didn't pass. C didn't pass the conductor emission. Design B passed conductor, passed radiated, and we have 95 reach, 96 reach. Design A, bad in EMC, bad in efficiency. What you can do, if you just drop out the two components here, the two common mode choke, put the inductor instead, you have efficiency and you have quite good EMI. Or you can go by design B, and this is the compromise that you can do using the compromise from design B and C. Use something less switching frequency, not 400, not 200, only 350 kilohertz. Use the filter from design A, which was more like enough, and make it small and compact. You have to use 6-layer because the logic component, it won't be too squeezed by 4-layer, so he go by 6-layer, and with this passed all the EMC test. Some layout recommendation: if you make filter, please don't do stupid things like that. This is what happens if you push out routing. It is galvanic connected, but capacitor with such long track, don't put capacitor, save the money. You don't need it because no effect. If you have a capacity for filtering, put the pad and put the via. And much better, put 2 via. One single via is already 0.5 nanohenry. If you put 2 inductance in parallel, half inductance. 2 resistance in parallel, half resistance. Always a good thing to put for filtering capacity, 2 vias. And about this insertion for high frequency, okay, if you want to filter gigahertz, you will need to do that. If you don't need to filter gigahertz, you don't need to do this V for the high frequency. This is only request if you want to filter several gigahertz. For less than 1 gigahertz, you don't need to do, you can put it straight. But important, how to connect the capacity. Not long tracks and then round. More information you can get in these books. Trilogy, capacity book, even we have for this kind of micro modules and also for connectors and so on. LT Spice book. Please ask my colleagues in the field. The sales colleagues will be very happy to give you this book, and you can have more information on that. If you need to build a rack because you have an EMC lab or you want to have your own pre-compliant measurement, you can ask my colleague in the sales for these different racks on the wall or this pyramid, which you can turn it and you can move it with reels. Also, these different racks is possible to get them. Please ask my colleague in the sales what is the possibility to have these demo racks for you. If you want to keep in touch with me, please watch the YouTube videos. You can go on the YouTube, you can find some interesting videos, or get in touch with LinkedIn or with Twitter. I hope I was not boring too much, and thank you for your time for watching my webinar, and see you next time. Bye-bye.